Hi, I'm Antoine, and I will present our paper SuGaR, Surface-Aligned Gaussian Splatting for Efficient 3D Mesh Reconstruction and High-Quality Mesh Rendering. Using RGB images captured with a camera, the goal of novel view synthesis is to create a representation of the scene that is able to generate new images from any novel point of view. To solve this problem, 3D Gaussian Splatting proposes to use millions of tiny 3D Gaussian primitives to represent the geometry of the scene, as well as a new rasterization strategy tailored for 3D Gaussians to render images much faster than concurrent methods relying on volumetric rendering. Even though radiance fields allow for photorealistic rendering, for many tasks, 3D artists need an explicit representation of the surfaces, typically what we call a triangle mesh. Indeed, the mesh is still the default representation used in computer graphics, for many reasons. We also believe and show with our method that meshes can be excellent proxies for editing, sculpting, rigging, or animating 3D representations using traditional software. The standard practice for extracting meshes from radiance fields is to apply margin cubes. However, 3D produces millions of tiny and unorganized Gaussians when reconstructing real scenes. Margin cubes does not scale well to such tiny primitives and outputs meshes like this one with a lot of holes and artifacts. Moreover, even though some methods propose to extract meshes from nerves, these approaches can be very slow or inaccurate. With SuGaR, we introduce a method that extracts accurate and editable meshes from 3D Gaussian splatting representations within minutes on a single GPU. The meshes can be edited, sculpted, animated, composited, and rendered with very realistic Gaussian splatting rendering. Our approach involves the following three contributions. First, a regularization term that encourages 3D Gaussians to align with the surface during optimization. Then, a mesh extraction method that is scalable, fast, and preserves scene details, unlike margin cubes. Finally, a refinement method that binds 3D Gaussians to the triangles of the mesh, resulting in a hybrid representation. 3D Gaussian splatting reconstructs the geometry of the scene as a combination of many 3D Gaussians. Thus, it can be represented by the following density function, which is proportional to the PDF of a Gaussian mixture model. We show that in an ideal scenario where Gaussians would have limited overlap with each other, would be opaque, flat, and aligned with the surface, the density function could be simplified as the following d bar. In this ideal scenario, we can also define a distance function f. To regularize our 3D Gaussians, we simply minimize the distance between the actual density function d and the simplified density function d bar that should hold true if Gaussians were aligned with the surface. This regularization already works pretty well, but we show that we can push it even further by instead using the distance function f. For extracting a mesh from our surface-aligned Gaussians, we do not rely on margin cubes. Instead, we sample points and their corresponding normals on the surface of the scene, then use Poisson reconstruction to recover a triangle mesh. Specifically, we sample points on the visible part of an isosurface of the density function d corresponding to the mixture of Gaussians. Because the parameters of the Gaussians are explicit, sampling points on the isosurface of the density can be done very efficiently. Compared to margin cubes, our method is able to extract a mesh with much less holes. Moreover, thanks to our regularization, our full method greatly reduces the noise on the surface and produces a much smoother mesh. After extracting a mesh, we can bind new Gaussians to it and render the meshes using very realistic Gaussian splatting rendering. We simply texture the triangles of the mesh with very thin Gaussians. The parameters of these Gaussians are refined in the coordinate space of the triangle, so that they are automatically adjusted when editing or animating the mesh.